Hello and welcome to lesson number 29, Sums of Infinite Series. In our previous video, lesson 28, Sums of Finite Series, we discussed finite series. Series that had definite starting points, definite ending points, and a finite number of terms in between them. We could guarantee that the sums of these series would be finite, provided of course that each of the terms within the series were also finite. If you haven't seen that video, click this link in the top right here. For infinite series, however, even if all of the terms within the series are finite, we cannot guarantee that the series' sum itself is finite. It could be infinite. It could also be a non-specific value. In this lesson, we have two words that we use to describe these kinds of series. They could either be convergent or divergent. To be convergent is to have a finite, definite, definable value. If we consider the sum of this series starting from the first term, the second term, the third term, and we start adding terms one by one until infinity, if the total sum approaches a definite value as we start adding more and more terms to infinity, then we can say that that sum is convergent. It has a finite, definite, known value. The opposite is a divergent sum. Divergent sums contain all the sums that do not have this property, as in the property that where you start adding in an infinite number of terms, the total sum approaches a certain value. If the total sum doesn't approach a certain value, it is called a divergent sum. There are of course different types of divergent sums. We could have divergent sums that diverge to a certain infinity. For example, the sum of positive integers from 1 to infinity. 1 plus 2 plus 3 plus 4 plus 5 and so on gets bigger and bigger and bigger as you add more and more terms. Due to this sum is going to approach infinity. It is therefore a divergent sum whose sum is infinite. Another example of divergent sum is a divergent sum where the value oscillates in between values. Either it could be oscillating between positive and negative values, or maybe 2 or 3 or more specific values. For example, if we consider the sum sigma of, let's say, sigma from r equals 0 up to infinity of negative 1 to the power of r, this sum is going to be the sum of the value of negative 1 to the power of r for r equals 0, which is going to be 1, plus the value of negative 1 to the power of r for r equals 1, which is going to be negative 1, plus the value for r equals 2, which is going to be positive 1, minus 1, plus 1, minus 1, and so on. We can see that the sum is oscillating. If we consider an odd number of terms, say for example 5 terms, by cancelling this thing all the way up to here, we can see that our sum is going to contain a certain number of 1s and one less number of negative 1s. Therefore, if we start cancelling the 1s and negative 1s, this will cancel this will cancel this, and we will be left over with a single 1. Therefore, for this sum, if we consider an odd number of terms, we will have a total sum of 1. If we instead consider an even number of terms, say for example 4 terms, then we would have an equal number of 1s and negative 1s. Adding all of these together, all the 1s and negative 1s would cancel, leaving us with a sum of 0. Therefore, this sum here, the sum from r equals 0 up to infinity of negative 1 to the power of r, is oscillating between the values of 1 and 0. Therefore, if we take an infinite number of terms and we add them all together, we cannot give a definite value for that sum. Therefore, it is also a divergent sum. To formalize this, we could say that if the limit as n approaches infinity of the sum from r equals some starting value, let's say a, up to n of the terms which I'm going to represent with t of r is some limit L, where L is an element of the real numbers, then we can say that that total sum, the infinite sum from r equals a up to infinity of t of r, is going to be a convergent sum. So running through this again, we can see that the limit from n approaches infinity indicates that we're summing an infinite number of terms. This upper bound n is going to infinity, meaning that the total sum is going to sum an infinite number of terms starting from r equals a up to infinity. For each of those terms, it's going to evaluate t of r, as it's going to be t of a plus t of a plus 1 plus t of a plus 2 and so on up to infinity, and if that total sum is equal to L, where L is some element of the real numbers, then we can say that the series overall is convergent. This of course rules out the possibility of having an infinite value, since if L was infinite, it would not be an element of the real numbers. Similarly, this also rules out the case where we don't have a specific value, or the value could be oscillating between multiple different values, since in that case the limit would not exist. There would not be a single value that we could put on the right side of this equation to satisfy it. Therefore, all other cases are called divergent. As in, the sum doesn't approach a definite value. No matter what other value it may approach, it is going to be called divergent. We can test for the convergence of a sum in many different ways. Here are 3 simple examples for convergence tests that we can use to find whether a sum is convergent or divergent. The first one is to check whether the terms get smaller. If the terms don't get smaller, as in they are either equal to each other or they get bigger and bigger, then we can say that the sum is going to be divergent. Why? Well, think about it. If the terms are all equal and have the same sign, then we're just adding a bunch of values together infinitely. Due to this, we're going to get an infinity. If they are all equal to each other but they have, like, let's say for example alternating signs, then they're going to have an alternating sum and therefore are not going to have a specific value as we take the number of terms added together to infinity. Therefore, once again, divergent. If instead of being equal, the terms get bigger and bigger, then we can say that as they get bigger and bigger, if they have the same sign, then adding them all together will give you an infinite value. Instead, if they have alternating signs, then if you have a plus and a minus and plus and a minus or something like that, then you're going to be above the number line, below the number line, above the number line, below the number line, something like that, meaning that you're never going to settle on a particular value. So therefore, we need the terms to get smaller and smaller as we go on. To write this in a more formal mathematical sense, we would need the condition that as the limit of n approaches infinity, we would need the condition that t of n, where t is the certain number of term, the numbered term, and the number of the term is n, is going to be equal to 0, as in the terms get smaller and smaller and approach 0 as we take n to infinity. The second thing is the divergence convergence test using upper or lower bounds. If we can find some other sum where, for example, every single term, let's say the sum that we are considering is t dash, it's the bounding sum, where t dash of r is greater than t of r, or maybe we could say greater than or equal potentially to t of r, then it would be an upper bound, since the sum of all the terms t dash of r is going to be greater than the sum of all terms t of r, since every single term t dash of r is greater than every single term t of r. This would be an upper bound. Or we could have the case where we have a lower bound, in which case we have t dash of r being less than or potentially equal to t of r. Now in this case, of course, it's a lower bound. For the convergence divergence testing, we can say that if the upper bound, this bound here, is a finite value and this value is something less than that, provided of course is bounded by something, let's say the positive axis, so let's say greater than or equal to 0, and same thing here, this is greater than or equal to 0, something like this. In this case, if we have this condition and the upper bound is a finite value, then we can guarantee that the actual thing we're looking for, the sum of all terms t of r, is also a finite value, since a finite value is the only value that could be less than another finite value and greater than 0. Similarly, if our lower bound is infinite, then we could say that this thing right here is also infinite, as in it is divergent. Because if our lower bound is some infinite value, any value greater than or equal to an infinite value must also be infinite. Therefore, we can test using upper and lower bounds to see whether a sum is convergent or divergent. If the sum is convergent, we would have some upper bound which would also be convergent. Similarly, if we have a divergent sum, then there would be some other lower bound which would also be easily proven to be divergent. The important thing here is that the t dash would be easier to prove than the t of r to be divergent or convergent. And from this, we can easily prove that t of r is either convergent or divergent. Third and final method that I'm showcasing here is the integral test. Integral tests can be used to establish lower bounds and upper bounds for certain functions, and by doing so, we can find whether the sum of a certain series is infinite, or if it is finite, we can find an upper bound and a lower bound for it, which can be used to approximate the value of the sum. So basically, the basic idea that you need here is that we have some function that is either identical to this function that we are using for our terms, or some function that is less than or greater than our function that we are interested in. And given that function, we want to integrate that function from our starting value, let's say a, up to infinity. So we want to do the integral from a up to infinity of our function, which I'm going to represent with t of x dx. We want to consider this integral If this integral is going to be infinite, then we know that if our original function that gives us the sum of terms is greater than that, it is also infinite and therefore divergent. If instead our sum is lower than our given integral and the integral is also finite, then we know that the sum itself is finite and the integral can be used as an upper bound for that sum. Similarly, if we find some function that is always less than our certain series that we're interested in, then we can also find a lower bound for our series using the same exact method. So there are some methods that we can use as convergence tests on our functions. It should be noted that some of these convergent tests only work in one way and sometimes will give false positives or false negatives. For example, this first test here, do the terms get smaller? If the terms don't get smaller, then we can guarantee that the sum that we're going to get is going to be divergent. It's going to be sum infinity or an oscillating sum. However, do the terms get smaller? If that is a yes, as in we have the condition that the limit as n approaches infinity of t of n is equal to 0, that is not sufficient for us to conclude that the sum is in fact convergent. You can see it only worked in one direction. A counter example for this to show that it only works in one direction is the sum sigma r equals 1 up to infinity of 1 divided by r. This is the sum of 1 divided by 1 plus 1 divided by 2 plus 1 divided by 3 plus 1 divided by 4 plus and so on and so forth. We can see that each consecutive term is less than the previous term. A half is less than 1, a third is less than a half, a fourth is less than a third, and so on. If we take the limit as n approaches infinity of 1 divided by n is in fact 0. Since if you have a bigger and bigger number on the bottom, we're going to have 1 divided by a really big number which is going to be really close to 0. So therefore the limit as n approaches infinity of 1 divided by n is 0. So therefore we have that condition as well. However, this sum is in fact divergent. It approaches infinity as you keep adding terms. We can show that it approaches infinity and therefore that is divergent by using a lower bound test. The lower bound we're going to be using is going to be based off of the structure of this sum. Consider this sum. This sum is equal to 1 plus a half plus a third plus a fourth plus, I'm going to write a few more terms to get an idea, plus a fifth plus a sixth plus a seventh plus an eighth plus and so on and so forth. Now consider each of these terms and consider the 1 divided by 2 to the power of n's that we have in this series. Here we have a 1 divided by 2 to the power of n, here we have a 1 divided by 2 to the power of n, and here we have a 1 divided by 2 to the power of n. What I'm going to do is write a different sum s, which is going to be 1 plus a half, and then for every term that is not 1 divided by 2 to the power of n, I'm going to write it as 1 divided by 2 to the power of n, where the value is the next 1 divided by 2 to the power of n that is smaller than our given term. For example, consider 1/3. 1/3 is little bit bigger than the next 1 divided by 2 to the power of n, which is 1/4. So therefore I'm going to replace it with 1/4. So here instead of the third, we're going to replace it with the fourth. The next term is a fourth, so I'm going to leave it as that. As for the next term, 1 divided by 5 is bigger than the next lowest 1 divided by 2 to the power of n, which is 1 divided by 8. So I'm going to replace the 1 divided by 5 with 1 divided by 8, or 1 divided by 2 to the power of 3. The next term 1 divided by 6 is again based on the same condition, greater than 1 divided by 2 to the power of 3 or 1 divided by 8. So I'm going to replace it with 1 divided by 8. The next term is also less, so I'm going to greater this, so I'm going to replace it with 1 divided by 8, and 1 divided by 8 is going to remain as 1 divided by 8. We can see that when we do this replacer, the sum here has terms that are common, as in the terms that remain, which are going to be the terms which are of the form 1 divided by 2 to the power of n. But there are also other terms that have been replaced with 1 divided by 2 to the power of n's. Importantly, the 1 divided by 2 to the power of n's with which we replace them are in fact smaller than the original terms. This 1/4 is smaller than this 1/3, this 1/8 is smaller than this 1/5, this 1/8 is smaller than this 1/6, this 1/8 is smaller than this 1/7, and as we go forward, all of the terms that have been replaced are smaller. The terms that have not been replaced, of course, are equal. So this term is equal, this is equal, this is equal, this 1/8 is equal, and so on. So we have a bunch of terms that are equal, but we also have some terms in this sum that are less than. So we can say that every term in here is less than or equal to every term in this sum over here. Now, consider this sum on the bottom. Here we have a 1. we also have a half. We also have 2 1/4. If you add the 2 1/4 together, you get a half. We also after that have 4 1/8. If you add the 4 1/8 together, you get a half. Considering the continuation of this, after this we're going to have a total of 8 1/16. 1/9 is going to be turned into 1/16, 1/10 is going to be turned into 1/16, and so on, giving us a total of 8 1/16. Meaning that if we add them all together, we're going to get another 1/2. If we consider after that, we're going to have a total of 16 1 divided by 32s, which is going to give us another half, and then we're going to have 32 1/64s, which is going to give us another half, and so on. So we're going to have a continuous stream of halves being added together. Now then, we have a 1 here, and we have a continuous stream of halves that are being added together. If we have a continuous and infinite supply of these 1/2s, we can say that the sum S is going to be infinite. Therefore, S is divergent to infinity. Now, considering S and its divergence to infinity, we know that every single term in S is less than or equal to every single term in this above sequence here. So therefore, if each individual term is less than or equal to each individual term in here, we can say that the total sum S is less than this total sum here. But we already proved that S is divergent to infinity. So if S is divergent to infinity, we can see that if this sum is greater than or equal to S, we can see that this sum is also going to be divergent to infinity. Since if a value is going to be greater than an value that is going to go to infinity, that value itself must also go to infinity. So therefore, we can say the sum from r equals 1 up to infinity of 1 divided by r is going to be divergent. It actually diverges very slowly, extremely slowly, but it does diverge to infinity. If you add enough terms, you can get to any number in the real numbers and pass all of them and go to infinity. So therefore, even though this sum here satisfies our rule where each of the terms gets smaller and smaller, as in the limit as n approaches infinity of that term, which is 1 divided by n, is equal to 0, the function itself, when you add all of the terms together, is not going to be convergent. It is divergent to infinity. Interestingly, if this power of r down here is anything greater than 1, the series will converge instead of diverging. For example, if we have the sum from r equals 1 up to infinity of 1 divided by r squared, we can see that the power here is something greater than 1. And due to this series here will actually converge. This particular series converges to a nice value of pi squared divided by 6. We're not going to be deriving where this value came from or how to get it, but we're just going to be talking about it, saying that it's a nice value and that it converges. Similar to this, if you have any power of r like this, which is greater than 1, our series will converge. For example, if we had r equals 1 up to infinity of 1 divided by r to the power of 1.00000001, anything like this will converge to some finite value. However, if you don't have this 1 at the end, if you just have just a power of 1, this will diverge. We can prove that if we have a power of r anything greater than 1, then our series will converge using integration. So what we're basically going to prove is that if you have the sum from r equals 1 up to infinity of 1 divided by r to the power of n, this will converge if n is anything greater than 1. To do this, what we're going to do is to consider the integral, consider the graph, consider some areas, and then apply principles to figure out that if the power is anything that is greater than 1, then we're definitely going to have a finite value for our sum. So to do that, here I've drawn a graph. It's a y and x graph with y equals 1 divided by x to the power of 1 plus delta, where delta is some positive value. Since delta is some positive value, 1 plus delta is definitely bigger than 1. And due to this, we have the form where we have a graph of y equals 1 divided by x to some power which is greater than 1. What I want you to do now is to consider each of these points that I've marked that are the points running along the integer values of x on the graph y equals 1 divided by x to the power of 1 plus delta. Each of these points correspond to substituting the corresponding value of x, which is in this case 1, 2, 3 and so on, into the function y equals 1 divided by x to the power of 1 plus delta. So therefore, the y value here is going to be y equals 1 divided by 1 to the power of 1 plus delta, which I'm actually going to write on this side as 1 divided by 1 to the power of 1 plus delta. This is going to be 1, but we'll just ignore that for now and go to the next one. For 2, for x equals 2, this values y, the y value of this point is going to be 2 to the power of 1 plus delta. For this point here, it's going to be 1 divided by 3 to the power of 1 plus delta. For this point here is going to be 1 divided by 4 to the power of 1 plus delta, and so on. Now, consider the area of the rectangles that I'm drawing out here. For each of these rectangles, we can see that the horizontal distance or the base length for each of them is 1. Since from 0 to 1, the distance is 1. From 1 to 2, the distance is 1, and so on. So for each of these rectangles here, the base length is 1. What about the height? The height, since we are starting from 0, is going to be the y-coordinate of this point here, and this point here, and this point here, and so on. So from that we can see the height is going to be, for this rectangle, 1 divided by 1 to the power of 1 plus delta. For this rectangle is going to be 1 divided by 2 to the power of 1 plus delta, and so on downward. If we now consider the areas of these rectangles, for this rectangle here, area is going to be equal to the base length times the height, which is going to be 1 times 1 divided by 1 to the power of 1 plus delta. So therefore, this area is also going to be equal to 1 divided by 1 to the power of 1 plus delta. Similarly, for this rectangle here, this rectangle has a base length of 1 and a height of this. So therefore, this thing is going to have an area of 1 divided by 2 to the power of 1 plus delta. The next one, of course, is going to have an area of 1 divided by 3 to the power of 1 plus delta, and so on. Consider the total sum of all of these areas. The total sum of all of these areas is 1 divided by 1 to the power of 1 plus delta, 1 divided by 2 to the power of 1 plus delta, all together added together. We can write this in a common form and say, using sigma notation, that the area involved here is the sum from r equals 1 up to infinity of 1 divided by r to the power of 1 plus delta. This is the value of the total area of each of these rectangles as we go to infinity. Now, consider how the area of these rectangles relates to the area under the curve as in the integral of this graph. We can see that in addition to the rectangle areas, the integral of the graph or the area under the curve, this area that I'm highlighting here, has some additional bits. This bit here, this bit here, this bit here, this bit here, and so on are additional to the total area of the rectangles. Due to this, we can see that the integral of this graph is something that is greater than the sum of each of these rectangles areas. So therefore, if we consider the rectangles areas and consider the integral of the graph, we can see that the integral is greater. For that reason, I'm going to put a less than sign here and say that this sum is less than the integral of this graph, and if we consider what the integral is, it would be the integral from 0 up to infinity of 1 divided by x to the power of 1 plus delta dx. So therefore, this is less than the integral from 0 to infinity of 1 divided by x to the power of 1 plus delta dx. At this point, for us to prove that this thing on the left is finite, we're going to have to make one small adjustment to this inequality. The small adjustment we're going to do is to ignore the area from 0 to 1 of both the graph and of the sum. The reason that we're doing this is because of the fact that the area under the curve from 0 up to 1, as in the integral from 0 to 1 of 1 divided by x to the power of 1 plus delta dx is actually infinite. The area under the curve here that I've highlighted is infinite. As it turns out, the rest of the curve's area, this area here, from here up to here to infinity, is finite. So what we're going to do is to ignore this little bit here, the little bit to the left, and only consider the area from this point here onward. Now, this won't cause any problems for our summation logic and saying that this sum here is finite. The reason that it's not going to have an issue with this sum being finite is because the term we're excluding, the very first term, is guaranteed to be finite. This bit here, this area, is a finite value. We're just going to consider this bit separately and consider only the rest of it, the entire rest of this function, as in all of the sums of all of these rectangles to infinity, separate to this one area here. So what we're going to do is to consider the areas of all the rectangles after that point, as in all of these areas under the curve here, and the area as in the integral of the curve from 1 up to infinity. Considering those two instead, if we remove the very first term, for the sum, our sum is now going to be the sum from r equals 2 up to infinity of 1 divided by r to the power of 1 plus delta. As we can see visually, this area is less than the area under the curve of this graph, which is going to be the area starting from 1 and going up to infinity of the curve. So that's going to be integral from 1 to infinity of 1 divided by x to the power of 1 plus delta dx. So what we're going to do here is to show that this bit on the right here is finite, and therefore this bit on the left here is also finite. And then to that we're going to add the finite value, which is the first term, to show that the whole series in total is also going to be finite. So doing exactly that, considering the integral on the right side here, this integral is the integral of from 1 to infinity of 1 divided by x to the power of 1 plus delta. Since the power here is on the denominator, we can write this as being equal to the integral from 1 to infinity of x to the power of negative 1 minus delta dx. Now, since this power here is not equal to negative 1, we can use the power rule for integration. The power rule for integration states that the integral of x to the power of n dx is equal to x to the power of n plus 1 divided by n plus 1 plus c for n's that are not equal to negative 1. So, we're going to be applying this rule to this thing here, and if we do so, we can see that what we get is going to be the integral evaluated from the two limits, which are in this case 1 and infinity, of this thing which we're going to take. This thing's going to be raised to this thing's power negative 1 minus delta plus the additional 1, so it's going to be x to the power of minus 1 minus delta plus 1 divided by minus 1 minus delta plus 1. We can see here the minus 1 and the plus 1 cancel, so we can cancel those two out. The minus 1 and the plus 1 cancel here as well as in the exponent. So this minus 1 and this plus 1 cancel, leaving us with just this integral here to evaluate. We have x to the power of minus delta divided by minus delta to be evaluated from negative 1 up to infinity. Now, evaluating this thing, we can see that this is going to be the values of what we do when we substitute infinity to the power of minus delta divided by minus delta minus the value when we substitute 1 to minus delta divided by minus delta. Now, infinity to a negative power. In this case, infinity just means a really big number, and a really big number to a negative power is going to be a really small number. For infinity, if we make a really big number, this number divided by this number rather is going to be 0. So due to that, this term here is 0. So here we have 0, and then this minus and this minus will cancel to give us a plus. So we have plus 1 to the power of negative delta, which is 1, and then divide by delta. So therefore, our sum here is 0 plus 1 divided by delta, which is going to be 1 divided by delta. So therefore, the integral from 1 up to infinity is 1 divided by delta. Going back up here, we can see that the sum from r equals 2 to infinity of 1 divided by r to the power of 1 plus delta is going to be less than the value of this integral, which we just found to be equal to 1 divided by delta. Now, consider adding to this the very first term. We can add the very first term to both sides. The very first term is going to always be 1 divided by 1 to the power of 1 plus delta. Adding that to both sides, we can see we get on the left hand side the sum starting from 1 in this case to infinity of 1 divided by r to the power of 1 plus delta, since we have the very first term when r is equal to 1. And on the right side, if we add the very first term is 1 divided by 1 plus 1 to the power of 1 plus delta, which we're going to write as 1 over delta plus 1 over 1 to the power of 1 plus delta. Now 1 to the power of 1 plus delta is going to be equal to 1, since 1 to the power of anything is going to be 1. And then 1 divided by 1 is going to be 1. So therefore we can actually erase this and directly say that the sum from r equals 1 up to infinity of 1 divided by r to the power of 1 plus delta is some value which is less than 1 divided by delta plus 1. Now, since this 1 divided by delta plus 1 is some finite value, we can certainly say that this sum here is going to evaluate to some finite value. If it evaluates to some finite value, it is going to be convergent, provided of course that it's not oscillating. In this case, since all of the terms here are going to be positive, it is not oscillating, it is instead converging to a direct value which is somewhere less than 1 divided by delta plus 1. In mathematics, as it turns out, sums of this form are actually listed under a common function known as the Riemann-Zeta function. The Riemann-Zeta function has a symbol that looks a bit like that. It takes an input s, and it is basically the sum from r equals 1 up to infinity of 1 divided by r to the power of s. So here we can see that this sum is exactly of the form that we've been dealing with so far, and the Riemann-Zeta function of s converges when s is some value which is going to be greater than 1. So basically the condition that we've seen from the above integration step. The Riemann-Zeta function is not part of our syllabus, however it's an interesting bit of mathematics, which is why I put it as part of the video. So that's going to be all on that. Let's now move on to the next section of the video, which is going to be on common sums that we find in infinite summation. So basically, common infinite sums. For our first common infinite sum, we're going to be discussing infinite geometric sums. So basically sums that are of the form s equals some first term a plus a times some ratio r plus a times that same ratio r squared plus a times r cubed plus a times r to the fourth, and so on and so forth. We can see that there's a common ratio in between the terms of r. The first term, the second term is r times the first term, the third term is r times the second term, and so on and so forth. The way that we find the value of this infinite sum is by multiplying the entire sum by r. On the left hand side, we get r times s, and on the right hand side, this term multiplied by r becomes a times r, this term multiplied by r becomes a times r squared, this term multiplied by r becomes a times r cubed, and then a times r to the fourth, a times r to the fifth, and so on. For this kind of sum to converge, we need the condition that this r converges downward as we take higher and higher powers of r. As in, we need the condition that the limit as n goes to infinity of r to the power of n is equal to 0. This basically implies that the absolute value of r must be less than 1. So let's take that the absolute value of r is some value less than 1, as in r is some value that is in between 1 and negative 1. So given that, let's try and evaluate the value of this sum s. In order to do that, what we're going to do is take a look at this sum, take a look at this sum, and subtract the second sum from the first sum. So if we subtract that like that, we can see that this AR cancels for this AR. So here these two cancel, these two cancel, these two cancel, and so on and so forth all the way down. But we have to consider the very last term to still be existing, because if we consider cancelling like this, we can see at each step this term here remains. However, if r to the power of n as the limit as n goes to infinity of r to the power of n is 0, we can see how even though we are cancelling like this and each time a term is remaining, the term that remains approaches 0. So therefore, if we keep cancelling like this, eventually the very last term left over is 0. So due to that, after all of this cancellation, the value that we have on the right side is exactly equal to just a. Because whatever a to the power of n that a times r to the power of n that we have left over is basically 0. So we have just a on the right hand side. As for the left hand side, we can see we have s minus r times s, which is going to be 1 minus r times s. So 1 minus r times s is equal to a, meaning that s is equal to a divided by 1 minus r, provided of course that we have the condition that this value r has an absolute value which is some value less than 1, as in the value of r is some value in between negative 1 and 1. So given this, a geometric series of this form will converge to a divided by 1 minus r. The next type of simple infinite sum that we can have is a telescoping sum. So if we go down here and consider what that would be, a telescoping infinite sum would be a sum of the form sigma r equals 1 up to infinity, and for our simplest case, let's consider a telescoping sum that goes v of r plus 1 minus v of r. There can of course be other types of telescoping sums, but this is the simplest one. The next term minus the previous term. If we consider this sum, we can see how this sum is, for the first term, v2 minus v1, so it's going to be v2 minus v of 1, and then plus v of 3 minus v of 2, and then plus v of 4 minus v of 3, plus, let's do one more, v of 5 minus v of 4, and so on and so forth until the very last term, which in this case doesn't exist, but let's imagine it exists. It would be plus v of, let's say, n minus v of n minus 1. Now, consider what this means. This means that all of the terms in the middle are going to cancel out. We're just going to have that one v1 term at the top, and from the other side, all the other terms are going to cancel out except for the last term. So we're going to have the very first term and the very last term. Now, the very first term is of course going to be some finite value, because for finite numbers we are assuming that this function v gives us finite outputs. So therefore, v of 1 is going to be a finite value. This bit, on the other hand, cannot be guaranteed to be a finite value, since its input is going to be infinite, since we are going all the way up to infinity. So what we need to do is make sure that this final term is in fact going to converge to some value, or is just 0. So either this thing converges to some finite value or it just goes to 0. So we need the limit as n approaches infinity of v of n to be equal to some limit where that limit is an element of the real numbers. If we have this property, then the last term in our sum for our telescoping series is going to be finite, and we also need our first term to be finite, but that's kind of, it goes without saying. We always generally have this first term, as in the low input terms of our telescoping sums, to always be finite. So this term needs to be finite. If this term is finite and this term is also finite provided by this equation here, then we can guarantee that this overall equation is going to be finite. And therefore, it's going to be finite, and if we look at its value, it's going to be v of n, where n goes to infinity, minus v of 1. So if we write that more formally, this sum, the sum as r goes from 1 up to infinity, so if I write this nicely, sum from r equals 1 up to infinity of, in the simplest case, v of r plus 1 minus v of r, is going to be equal to the value of the limit, which I'm going to write directly as the limit as n approaches infinity of v of n minus v of the very first term, v of 1. So this is going to be the value of our telescoping sum. Of course, if you have other more complicated telescoping sum, like let's say v of r plus 2 plus v of r plus 1 minus something like that, or maybe v of r plus 2 minus v of r plus 1 and then plus v of r or something like that. I don't know, it could be anything. But if you have that kind of telescoping sum, you need to make sure that the values of the sum as you take n to infinity are some finite value, as in they are convergent, and then you can subtract off of that the very first terms. Well, it depends on the structure of your telescoping sum, and you can get a finite convergent value for your telescoping sum. Our next and final type of convergent sum that we're going to be talking about before moving on to questions is going to be the type of convergent sum where you have a function for the partial sum. What I mean by partial sum is if you have the sum from r equals some starting value, let's just say 1 for simplicity, all the way up to n of some function, let's say v of r, if this sum can be written in closed form as another function, let's say f of n, as in f of n equals this sum here, if we can write something like this, then if we have a convergence property, then the sum from r equals 1 up to infinity of v of r would simply be equal to the limit as n approaches infinity of this function f of n. So we need this thing to be a convergent sum, and if that's the case, then if f of n gives the partial sum up to n from r equals 1 up to n of v of r, then we can say that the sum to infinity, the infinite sum of v of r, is equal to the limit as n approaches infinity of that f of n. This is of course kind of self-explanatory if you really think about it. Like here, this is just the value of the sum for a really large n. So if we take this really large n to infinity, as in by doing this is basically the same as taking this n to infinity by taking the limit as n approaches infinity. So it's kind of self-explanatory if you really think about it, but this is a common way that we can find the infinite sum of a particular series, if we know a common formula for a partial sum of that series. Let's now move on to an exam question and conclude this video. The exam question we have here is from the 2024 A-Level Combined Mathematics Paper 1 Part B. It is question number 12b. What we're going to be doing is solving the entirety of this question. At the start it says, let u of r be 1 divided by r times r plus 2 times r plus 4. It then says that f of r to be 1 divided by r times r plus 2, for r being an element of the positive integers. When you see this, you can get a hint that you're probably going to need some kind of summation to do this question. Now, moving forward, it says that determine the value of the real constant a such that f of r minus f of r plus 2 is equal to a times u of r, for r being an element of the positive integers. So here we're establishing a relationship. This relationship might remind you of a telescoping series. In fact, this is going to lead us to a telescoping series. So it says we have to find the real constant a such that a times u of r, or a times this, is equal to this. We'll do that, and then after that they're asking us to hence show that the sum from r equals 1 up to r equals n of u of r is equal to 11 divided by 96 minus this bit, for n being an element of the positive integers. So here what we're going to be doing is using the telescoping property of our sum in order to find it in terms of the first terms and the last terms. This is probably the second to last term, and this is probably the last term, and this bit is probably the sum of the first terms. Now, moving on, it then tells us that we need to show further that the infinite series, the sum to infinity from r equals 1 to infinity of u of r, is convergent, and find its sum. And finally it says find the real constant m such that the limit as n approaches infinity of the sum from r equals 1 to n, which is basically the sum from r equals 1 to infinity of m times u of r plus u of n plus 1 minus r is equal to 11 divided by 32. So let's start at the beginning and slowly work our way through this question. At the start we say let u of r be this thing and f of r be this thing, and determine the real constant a such that this equation holds. Let's now find the real constant a by substituting the values into this equation here. F of r is going to be substituted with this, and f of r minus r plus 2 is going to be substituted with this thing, with r substituted as r plus 2. Going down, if we do that, we have u of r being equal to 1 divided by r times r plus 2 times r plus 4, and f of r being equal to 1 divided by r times r plus 2. Now, going down here, if we consider f of r minus f of r plus 2 and say this is equal to a times u of r, what we're basically saying is that 1 divided by r times r plus 2 minus, and then here we have 1 divided by, instead of r we need to substitute r plus 2, instead of r plus 2 this r would be replaced with r plus 2, and we had r plus 2 plus 2, which is going to be r plus 4. So r plus 4, and this is equal to a times 1 divided by r times r plus 2 times r plus 4. Now, we can see here that these two could be taken into a common denominator. To do so, this needs to be multiplied by r plus 4, and this needs to be multiplied by r. Doing so, we get an r plus 4 minus r divided by r times r plus 2 times r plus 4 being equal to a times 1 divided by r times r plus 2 times r plus 4. Since neither of these denominators is equal to 0, we can cancel them out, leaving us with just an a on the right side and an r plus 4 minus r on the left hand side. Cancelling this plus r and minus r, we can see this equates to 4, meaning that we get the result that a is equal to 4. Hence we have solved the very first question, which is to find the real constant a such that that equation holds. So now we have found that the real constant a such that f of r minus f of r plus 2 is equal to a times u of r is equal to 4. The next part of the question asks us to hence show that this partial sum from r equals 1 up to n of u of r is equal to all of this stuff here. In order to do this, what we're going to do is replace u of r with this bit over here by substituting the value of a into this equation and rearranging it to get u of r, and then after substituting we're going to use the fact that this right here is a telescoping sum in order to find an expression which is going to give us this exact equation here. So let's go down and do exactly that. First off, with our value a equals 4, we can now say that 4 times u of r is equal to f of r minus f of r plus 2 from the equation we were given. We can now rearrange this to get that u of r is equal to 1/4 of f of r minus f of r plus 2. This now gives us that if we take the sums, the sum from r equals 1 up to n of u of r, it would be equal to 1/4 of the sum from r equals 1 up to n of this stuff, which is going to be f of r minus f of r plus 2. Here we can see that this right here is going to be a telescoping sum. What we're going to do next is consider certain values of r, write out a few terms, cancel out a few terms, and see what's left over, and using that, find this thing that we have on the left in terms of the telescoping sum on the right. So writing down a few terms, let's consider the sum r values. Let's consider the r values r equals 1, r equals 2, r equals 3, and let's also on the other side consider r equals n minus 2, r equals n minus 1, and r equals n. These are the first two values of r that we're going to have in this sum, and these are the last two values of r that we're going to have in this sum. Now, considering this, on the left hand side, u of r is just going to be on this side u of 1, u of 2, u of 3, dot 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 all the way down, and over here we're going to have u of n minus 2, u of n minus 1, and u of n. On the other side, however, this is going to be equal to a certain bunch of terms. If we consider terms involved here, we have a 1/4 in all of them, so I'm just going to quickly write down the 1/4 in all of them, and then we can get on to the actual part that we're interested in. So 1/4 in all of them, and considering the thing on the right side, we have f of r minus f of r plus 2. For r equals 1, this is going to be f of 1 minus f of 3. For the next term, this is going to be f of 2 minus f of 4. For the term after that, this is going to be f of 3 minus f of 5, and so on and so forth all the way down. On the other side, for the last term where r is equal to n, this is going to have f of n minus f of n plus 2. The term before that is going to be f of n minus 1 minus f of n plus 1. And then the term before that is going to be f of n minus 2 minus f of n. We can see here that this f of 3 cancels for this f of 3, this f of 4 would cancel for the next term of f of 4, this f of 5 would cancel for the next term f of 5, and so on downward. And from the other side, this fn cancels with this fn, this fn minus 1 would cancel for the term here, this fn minus 2 would cancel for the term up here. So all the terms in the middle are gone, and we are left with over here f1 and f2, and on the other side minus fn plus 1 and minus fn plus 2. So these are the values that we are left over with. They are all multiplied by 1/4, of course, so let's not forget that. We have 1/4 of f1, 1/4 of f2, minus 1/4 of fn plus 1, and minus 1/4 of fn plus 2. Let's now take all of this down and write the telescoping sum on the right side and this bit on the left side. So on the left side we have the sum from r equals 1 up to n of u of r, and on the right side what we have is 1/4 of all of this. So we have 1/4 of f1 plus 1/4 of f2, which I'm going to write as 1/4 outside and then 1/4 of f1 plus f2, and then minus fn plus 1 and minus fn plus 2. So this is what we have left over once we do the telescoping sum. We can now substitute these values in and write our final equation out. Doing so, recall that f of r is simply 1 divided by r times r plus 2. Therefore, if we write this down, the sum from r equals 1 up to n of u of r is equal to 1/4 times f of 1, which is going to be 1 divided by 1 times 1 plus 2, and then plus f of 2, which is going to be 1 divided by 2 times 2 plus 2, and then minus f of n plus 1, which is going to be 1 divided by that value, which is going to be n plus 1, and then times n plus 1 plus 2, which is going to be n plus 3, and then minus this bit here, which is going to be 1 divided by, if you do the math, it's going to be n plus 2 times n plus 4, and close bracket. Now, we can simplify all of this out and we'll eventually get this equation that we have been given over here. So let's do exactly that. Let's quickly simplify each of these terms. What we're going to do is to combine these two into a common fraction and then take this 1/4 into that common denominator and then take that 1/4 also into this thing and this thing. So if we do that, we get the sum of r equals 1 up to n of u of r is equal to, this bit is 1/3, this bit is, if we do the math, 1/2 times this is 1/8. So 1/3 plus 1/8, which is going to be 3 plus 8 divided by 3 times 8, or 11 over 24. 11 divided by 24 divided by 4 is going to be 11 divided by 96. So we get the 11 divided by 96. If you want, you could have those intermediate steps where this is 1/3, this is 1/8. So we get, if you cross multiply 8 divided by 24 plus 3 divided by 24, which gives us 11 divided by 24, and then that divided by 4 is 11 divided by 96. And then we get a minus 1 over this 1/4 goes in as a 4 times n plus 1 times n plus 3, and then on the other part this 1/4 goes in as 4 times n plus 2 times n plus 4, and this is of course 4 values of n which are element of the positive integers as the question said. So therefore we've proven that this sum from r equals 1 up to n of u of r is 11 over 96 minus 1/4 n plus 1 times n plus 3 minus 1 over 4 times n plus 2 times n plus 4. Now let's go and look at the next part of the question. The next part of the question is asking us to show further that the infinite series r equals 1 up to infinity of u of r is convergent and to find its sum. So we can actually do this by taking the limit as n approaches infinity of the sum from r equals 1 up to n of u of r, which we already know. This is based on the partial sum method that we had earlier. And then it says to find the real constants m such that the limit as n approaches infinity of r equals 1 up to n of u of m times u of r plus u of n plus 1 minus r is equal to this. So we'll be doing both of those. Going down here, if we consider the first part, what we want is the sum from r equals 1 to infinity of u of r, which is basically the limit as n approaches infinity of the sum from r equals 1 up to n of u of r, which we found here on the right side. So we can actually substitute instead of this bit here, all of this stuff here. So therefore what we're looking for is in fact the limit as n approaches infinity. I'm going to write this in small letters since there's a lot of stuff here, of 11 over 96 minus 1 over 4 times n plus 1 times n plus 3 minus 1 over 4 times n plus 2 times n plus 4. Now then, considering this limit that we have to evaluate here, this first bit is a constant term. Therefore, when you take the limit, nothing happens. It's just 11 over 96. As for this bit, we have 1 divided by 4 times n plus 1 times n plus 3. We have a lot of stuff of n on the denominator, nothing on the numerator. Therefore, the denominator is going to go to infinity as n goes to infinity. So we have 1 divided by infinity, which is 0, so plus 0. The second term here, which contains n on the denominator, is the exact same thing. If we consider taking n to infinity here, the denominator goes to infinity, the numerator stays the same, so we have another plus 0. Therefore, the sum to infinity is 11 divided by 96. So we've proven that the infinite sum from r equals 1 up to infinity, so basically the limit as n approaches infinity of r equals 1 to n of u of r is equal to 11 divided by 96. So therefore we can say, therefore sum from r equals 1 up to infinity of u of r is convergent because we found the value, it's a specific definite value, and its sum is 11 over 96. So there's our answer. We proved that part. Let's now move on to the next bit where they're asking us to find the value of m such that the limit as n approaches infinity of the sum from r equals 1 up to n of m times u of r plus u of n plus 1 minus r is equal to 11 divided by 32. For this thing, I think what we're going to do is to break the sum into two pieces and then take this constant out of this sum that we're going to create from this bit, and then we're going to have an equation where we can probably rearrange it, substitute values that we do know in order to find the value of m. So let's go down and do exactly that. Going down here, the limit as n approaches infinity of the sum as r goes from 1 up to n of u of r, actually m times u of r, and then plus u of n plus 1 minus r is going to be equal to the limit as n approaches infinity of the sum from r equals 1 up to n of m times u of r plus this bit, which I'm actually going to take into another limit as the limit as n approaches infinity of the sum as r goes from 1 up to n of u of n plus 1 minus r. So we have these two sums here. In this sum, we can take the m out as m times the limit as n approaches infinity of the sum from r equals 1 up to n of u of r. As for this bit, they've actually done a little trick here. If you look at the u of n plus 1 minus r and consider the values this can have, if we go from r equals 1 up to n, for r equals 1, this is going to be, if we just write this down here, r equals 1 up to n of u of n plus 1 minus r. If we consider the values of r equals 1 is going to give us n plus 1 minus 1, which is going to be u of n. The previous one is going to be, actually the next one is going to be r equals 2, which is going to be u of n plus 1 minus 2, which is going to be the previous term, which is u of n minus 1. The term after that is going to be u of n minus 2, and so on. And for the final terms, u of n plus 1 minus r when r is equal to n minus 1 is going to be u of 2. So we have plus u of 2. And finally, when r is equal to n, we're going to have u of n plus 1 minus n, which is going to be u of 1. So therefore, we can see we have all the terms u of n minus 1, u of n minus 2, so on, all the way down to u of 1. Which means this sum is identical to the sum from r equals 1 up to n of u of r. So what we're going to do is to replace that. In exam setting, you probably need to show this logic, show this understanding that these two sums are equal before you substitute, but I'm going to substitute directly. Substituting directly, we have that this bit is the limit as n approaches infinity of the sum from r equals 1 up to n of u of r. Now, we have this bit in here twice. This bit is simply 11 over 96 as we showed earlier. Limit as n approaches infinity of the sum from r equals 1 up to n of u of r, or simply the sum from r equals 1 up to infinity of u of r, is 11 over 96. Therefore, we can substitute into these equations 11 over 96, meaning that m times 11 over 96 or 11 over 96 m plus this bit, which is 11 over 96, is the value we've been looking for. Now, if this is equal to this is equal to 11 over 32 as the question asks, then we have the equation 11 over 96 m plus 11 over 96 is equal to 11 over 32. We can cancel all the 11s out. This 11 cancels, this 11 cancels, and we have 1 over 96 m plus 1 over 96 equals 1 over 32. If we multiply everything by 96, we can see that m plus 1 is equal to 96 divided by 32. 96 divided by 32 is 3. So therefore, we have m plus 1 equals 3, meaning that m is equal to 2. So we have the equation there, m is equal to 2. And that is it. We have solved an entire A-level question based on sums, based on finite and infinite sums both. Here we have a lot of techniques that are being used. We've substituted, we've shown that we have a partial sum, and then we've used the limit of that partial sum to find the infinite sum, and so on. And we've even found a specific value of m where we can get the specific result. So that's going to be it for this video. If you have any questions, post them in the comments down below. Thank you for watching, and goodbye.